Okay, it's time. We can start. So welcome. It's nice to see many of you. I hope that also the one online can enjoy. So if you can see the title of my thesis is Uncertainty-Aware Interactive Imitation Learning for Robot Manipulation. And now in these 15 minutes, I will give you an intuition of each one of these terms, so you will know which the thesis is about, and you can follow better what's going to happen later in the defense. Let's start with the most important. What is a robot, right? For many people, a robot is the vacuum cleaner that is autonomously cleaning our house and can learn also, for example, to pick up the poop of misbehaving dogs. Or in the industry is machines that are designed to be very fast, for example, to pick and place for packaging operations. In the context of research, and in this thesis, we imagine a robot as a more general-purpose machine. So more like a humanoid that, like us, can do many things, not only one thing like cleaning the floor or pick and place, but will in general do more than that. In particular, we are relaxing some assumption of the human arm, like in a humanoid, and the dexterous hand, and we will only have, for example, a hand with two fingers that is the opposable and the index fingers to manipulate the word. And now you wonder, then, what is manipulation? Because this is about robot manipulations. And it can be any action of the robot that is, by applying forces on the environment, is changing its environment. You see here the robot is picking the peg, is inserting in the right outlets, and then is also using tools. For example, it can learn to use a cable to open a door, or has to wrap up the cable around the two pegs. However, up to today, the greatest part of robot manipulations is hard-coded by engineers. So there is a part where the engineers are coding the behavior we want to have, for example, the cleaning of the vacuum cleaners. On the other hand, what we want to do, our ambition is to get teaching the robots. You see in this picture, there is me dragging the robot around and showing the desired task that I want them to learn, that is inserting the probe in the right place. And by imitation, so what we call imitation learning, the robot says, okay, I understand what you want to do, and quickly updates its memory and learn how to repeat this motor skill. However, why we don't have robots serving us in daily tasks? Because robots, most of the times, make mistakes. For example, you see here, the robot was instructed to use the probe to extract the battery, but the result is just terrible. It didn't manage to do that. And this introduced the other word, that is interactive learning. So we want to correct robots, because if robots make mistakes, and we can see that, we can tell to the robot, look, when you're approaching the battery, please push more, because that will make the robot to actually extract the battery correctly. And then when the robot sees that and understands that, execute the task again, and you see that now the battery is actually perfectly removed. There is one missing word in the title of my thesis, that is the uncertainties. That is the most important, I believe, because robots make mistakes because most of the times they don't understand what we want them to do. They don't perceive the information that I want them to perceive. For example, the signal can be very noisy or conflicting, so the human can change their mind. Like you see in this case, the blue dots are actually not a smooth function, but also, most importantly, robots make mistakes because they don't have enough data to make prediction. You see on the boundary of these figures, the uncertainty is growing because we are giving the ability of the robots to tell us, sorry, I'm going to make a prediction, but I don't know if this prediction is correct. But when we want to use these models, this what we call the Gaussian process, we want, for example, learn some behaviors. So in this case, you see the human is showing that he wants to draw a letter G, and the robots understand that he's in the higher side of the picture, he has to go on the left. If he's going the lower side, go to the right, and so on and so forth. So if now we let the robot do the task, by following these streamlines, the robot will be able to actually start and draw a new G that is none of the one that was drawn by the user. However, you can notice that on the boundaries, when we go far away from our data, and we start to follow the path that the robot will do, this will look much more like a no. I say, okay, robots, you didn't understand that I asked you to draw a G and not a O. And the robots will reply, I'm sorry, but I'm telling you that I was not sure. You see that the uncertainty is growing when we go on the boundaries of the figures. So it's not fault of the robots, it's our fault that we are not giving the robot the possibility of doing what? Of rejecting its uncertainty. Let's see if this works. So if we can estimate uncertainties, we can also push the robot in the direction of minimum uncertainty. So the robots will always try to go in the direction of maximum comfort, and you see here you obtain these vector fields that are always converging close to the demonstrations, so it ensures that the robot is not doing stupid stuff and also is not doing dangerous stuff. But we want to do manipulations, so let's start showing some example. In this case, we see that the user is showing a kinesthetic demonstration, so he's dragging the robot around because he wants the table to be cleaned. And we expect the robot to learn that. However, if now we execute, we see the robot is okay, pushing, but not so well on the table. He got stuck there. But we learned that with interacting corrections, we can actually update the behavior. So the user with a teleoperation device say, no, here you need to go a bit higher. Or we will see in a second that the robot will get stuck again, and the user will say, no, here you need to push a bit down. And most importantly, when we approach the table, the user is going to say, if you are close to the table, please push, because pushing will ensure that you actually clean the table correctly. You see, after a few interactions, after a few corrections, we can obtain the results that could not have been obtained with millions of demonstrations, because the user is targeting the results of the mistake that the robot is making. I know that many of you are looking at the robots and thinking, I really would like to touch the robot and annoying him or them. And you see here, I'm actually doing that. So if you describe the policy of the robot in a certain way, the robot can live around us and be safe in the interactions. So it's not going to apply high forces, and it's going to always try to converge in the region of minimum uncertainty, so close to where I give the demonstration. In this case, I was showing how to unplug. But the most valuable thing the robots have to learn is to pick and place stuff. Because we do that all the time. We do that in the industry, and we want them to do also in the house. And in the industry, we know to do that quite well, very fast. We design machine to do that. But if now we want the robot to do that for us in a daily environments, we would like to pick stuff as humans will do. So approaching on the side without stopping and going fast, and then placing in the desired goal, like I showed you. And with kinesthetic demonstration, we can do that. However, this may be not fast enough. So what we do? We give corrections. But this correction may result in catastrophic effects. So the robot just goes very fast, and it knocks the object down, and this can result in having a lot of water on the table if the bottle is open. But we can give very fine corrections until the robot actually learns to do this task correctly. You see, by speeding up the motion slowly bit by bit and coordinating the hands at the right time, you observe that the robot actually managed to go from more than 12 seconds to under 3 seconds in performing this big task at not zero velocity. But one arm is not always sufficient. Sometimes you need to pick big objects. And you see, in this case, we say, okay, let's use two arms, because we want to handle a big object. It can be a luggage, it can be a crate in a supermarket scenario. And if the robot didn't learn correctly how to do that, I can actually give corrections. The robot executes and say, here we need to push a bit harder. And so the robot updates its behavior. And you see that after a few interaction with the robot, in this case are kinesthetic interactions, they are not teleoperated feedback, the robot say, cool, I learned, I know what to do that. There is a problem, many of you may wonder, that I am showing you tasks that work very successfully, but they work in one specific case with the object in a particular locations and with a particular goal. So something is missing. We want the robots to adapt to many situations. We don't want to show a demonstration every time that we have a new situations. So let's imagine we are in a supermarket and we want to use robots to do reshelving operations. We learned, we give a kinesthetic demonstrations, and this kinesthetic demonstration can result to be successful to learn to take the box of milk and placing it on the shelf. We can also make it fast, because now we know how to do it. We give correction, and bit by bit we make it faster. But as I said, we want to go towards generalizations, where if the object location change, if the shelf change, the shelf position change, this also will work. So how we do it? We do it like trying to, you can imagine, like you can look at these figures and imagine that there is a human teaching a robot how to draw on a flat canvas, but now the canvas is actually not flat anymore, and we want the robot to automatically adapt to this new situation. And what does it mean on the reshelving case? It can be that I give one demonstration of this scenario, okay? And then now the object position of the orientation changed, and also the desired position on the shelf changed. You see that without giving you a demonstration, just by knowing the geometry of the task, of where was the object, where is now, and when was the goal and where is now, the robot adapts its behavior. And this is important because this will relieve us to give them many 100,000 demonstrations, despite now is the trend in robotics. Okay, just give 1 trillion demonstration, and the robot will figure out. And I strongly disagree with that. This can be also used in nursing and caregiving operation. So you see here that the human is showing how to dress an arm, for example, when assisting elderlies. Let's see. Now the robot will try to execute again. And you see here is doing it fine, but then the arm position change. But we are tracking the arm posture, and we can use the same method and say, okay, if now I basically using the same theory, that going from these key points, and now not the object position, the goals, but are the arm, the hand, the wrist, the elbow, and the shoulder position, and you see that the robot adapting its behavior. And last but not least, we want the robot to clean. So let's see if it starts. We show how to clean a flat table because it's very simple. And then we say, okay, now just clean this other object that is higher. And the robot just will adapt to this new height or this different orientation. Let's see. And finally, also to shapes that are actually bumpy. In this case, the robot is using a point cloud that is perceiving from its camera point of view. To finish, the last chapter is about ambiguities, because sometimes when we give demonstrations, we're giving sometimes too much information. So in this case, we are teaching a robot how to pick the mag, but there is also a coaster there. So the robot doesn't know if we refer to the mag or to the coaster, because the robot is stupid. It doesn't have semantic understanding of the word. So when it has to execute again, they will face an ambiguity. Say, okay, wait, you want me to execute the motion with respect to the mug or to the coaster? And we experiment this also in a supermarket setting, where we were showing how to pick the crate, the cucumber, and place that in the crate of cucumber. But the robot doesn't know what is a cucumber, doesn't know what is an apple. It just say, okay, you place in this object in the crate of cucumber or in front of the crate of apple, and to me, they are both fine. But there is no fine if I switch the order, because now placing it in front of the crate of apple or place it in the crate of cucumber will disagree. They will not match as intentions. And you now must have learned that we want to give corrections to the robot when they make mistakes. So they face an ambiguities. They tell us, sorry, I don't know what to do. They just say, okay, go in this direction. Say, sorry, that was actually wrong. Go on the other direction. And then the robot say, okay, cool, now I understand. You want me to go on that goal, and removes any possible ambiguity. Time is up. So this is a scheme that is an introduction where I introduce my thesis and the different methods. You see there is the part that is the motor policies, where we learn the movements, and also the generalization policies, where we learn to generalize to different contexts and to resolve ambiguities. And there is the impedance controls, that what we use to control the robot that does. We want them to do the movements we want. And enjoy the defense. And I guess we can have 1-2 questions very quickly, if anybody is curious of anything. Javier? So for the arm manipulation, did you do it centralized or distributed? It's a very good question. It's centralized. It's centralized. We also have a coupling stiffness, so between the two arms. So we sure that if we perturb one arm, the other will also immediately follow. And so it's one controller that is managing the two arms. So they all the time know the state of the other and can compute the distance. So in that way, you can say, okay, there is a huge offset. I'm supposed to be at this offset. I'm going to pull in that direction. So it is centralized. Last question. Zlatan?
So based on all your years of experience you gained, what's the biggest challenge for robotics?
Yeah, this is a difficult question to ask. So I believe, since a year, a bit more, we've been doing these Roboton challenges where we cannot constrain and say, okay, in this lab environment, we know how we have markers to track the objects or OptiTracks. We want to do everything from a camera, sensors, and we want to obtain the same achievements before. I can tell you that this is where is going to be the highest limitations, because the uncertainty at that point, we are going to have a higher source of uncertainties, like can be the uncertainty due to the camera localizations and calibration, etc. And in general, I mean, we need to see if these robots can actually adapt to very big scenarios, like very different scenarios, where we actually able to not only grasp boxes at different positions, but also different shapes, completely different scenarios. So can we actually do that transfer learning from that situation to the other? Because that can gain us a lot of speed up and then using the robots in our daily life. That's what I think.